Good morning to all of you. So in the last class, we have seen about some idea about the isothermal graph, okay, and we have also seen about what are the different additional consideration on which the coal bed methane production, gas production, and the water production will depend. Okay. Today, we'll be starting after this, knowing all these conditions and the parameters. Today, we'll be starting with the how if you are not going to have a physical well for testing, but suppose you are having some earlier data or earlier information about this coal methane production or coal methane report. So how you are going to take the data and use it for your calculation, or suppose you are having a running well and you are collecting the data, and depending on what are the data you will be collecting and how you are going to calculate or estimate the gas transport or the gas storage mechanism, that we are going to discuss today. Okay. But as I have said earlier, that this subject is very much new to you, and until and unless you are totally aware of all this parameter very much in detailed way, which we will be discussing in the fourth chapter, I cannot go in a very deep exploration or deep investigation right now. Okay. When you will be completing after you have completed the fourth chapter, then only I'll be coming with all the experimental details and the other related journals to show you that how the works has been done. Okay. But for now, we'll be dealing with very brief and to the point discussions. Okay. And if you are having any trouble to understand, you can ask always the question. So in the last class discussion, desorption isothermal graph, the way it was discussed. Okay, is it clear to all of you? The desorption isothermal graph, which is collected from the desorption field canister testing, it is very important step to understand the isothermal test and all these errors. Okay, because there are other factors which will be coming, but if you are unable to understand this isothermal graph, whether it is adsorption or desorption, your basic consideration is not clear, then it will be very much trouble to you for understanding the other detailed information. Okay. So, with continuation of the yesterday's class, today we'll be starting with the acquiring and integrating data. Okay. So, acquiring or integrating data means, as I mentioned, that suppose what are the data you need to collect. Okay. If you read this text, okay, in the 2-3 pages, they have discussed in detail about what are the data you need to collect for production, for preparing the basic reservoir data, because you know that the production data is always going to depend on some of the basic reservoir data and obviously some of the production parameter. Just like the mining, if you know that in case of mining parameters, you are always going to discuss about the geological conditions and the other mining operational conditions. So summarizing these two, you are going to get the total geomining parameters for mining extraction. So similarly here also we need to have the basic reservoir data, which is obviously from the geological point of view or petrological point of view, and then you are going to see what are the additional production data they are going to consider. Okay. And then with this data, how we are going to do the calculation of the gas in place, that is the next step. So I'll be discussing briefly and referring to the table 3.1. Okay. All of you are requested to see table 3.1. Okay. Now in the table 3.1, you will see that there are various parameters which are very much inbuilt to the reservoir, or which is very much inherent to the coal properties, that are first discussed, and then the sources, how you will be collecting those data, or from where you will be able to get this data, those things are given. So let us start this. So this is table 3.1, sources of the data for analyzing coal bed methane reservoirs. Okay. Now, the permeability, the initial pressure means the initial reservoir condition. Okay, at what stage the reservoir pressure is lying there, and what is the initial water saturation. The permeability will be considered from, obviously, by sending the water channel pressure. Okay, and you know that the hydrofracturing testing, you will be able to send the water pressure, you will be able to measure the water pressure, and so you will be able to measure by Darcy's law, you will be able to measure the permeability in situ. In situ means in field. Then obviously the gas disruption pressure. Gas disruption pressure, you already have seen that the gas disruption pressure is the pressure beyond which the gases will start to dissolve. Okay, for any reservoir there is a point, it may or may not be going to produce the gases, depending on whether it is totally or partially saturated with the gas, okay, methane. But then if you are going to switch it to the suppose the gas is totally saturated, then the moment you are going to reduce the pressure, you will be getting some of the gas production with the water production also. Okay, so in that case, you know that whatever the gases and the water are coming out, okay, it will be in the based on the relative permeability condition, not the absolute, only the absolute permeability of the gases and the water. Okay, so the critical disruption pressure, or the reservoir disruption pressure, is defined as the pressure beyond which only the gases will be dissolving. Okay. Next is the pore compressivity. Pore compressivity is the internal pore volume compressivity. That means with the pressure, with the changing of the stresses, with the changing of the pore pressure as you are withdrawing water, how the water is going to, how the pore volume is going to change, whether it is going to decrease, whether it is going to increase, how much it is going to change in the shape. Okay, that those things. And you can see that most of the cases you will be able to get all those test data from the borehole well test. Okay, so borehole well test in the field, you have to do some water injection, and then you have to measure with the pump. Okay, you have to consider the permeability, and there are standard processes, and from there you will be able to get more of these parameters. Some of the parameters is obviously from the core test, just like the resorption isotope discussed yesterday. Then the sorbed gas content. Sorbed gas content, you know that it is totally summarizing of three component, summation of the three component. First is the loss gas component, second is the adsorbed gas content, and third is the residual gas content, which you cannot take out from the gases, okay, from the coal. Okay, whenever you are going to reduce the pressure, you will reach a point beyond which you cannot reduce the pressure. Okay, that pressure step is called the abandoned gas pressure. There is a critical disruption pressure, or the disruption pressure, and there is an abandoned pressure. Okay, beyond which you cannot reduce any pressure of the reservoir. And so the gas production is only possible, between this critical disruption pressure, or the disruption pressure, to the up to the abandonment pressure. Okay, next is the disruption time. Okay, disruption time, as you know, the sorption time or the disruption time, it is related to the 63.2% of the total disruption from the field disruption test. That's why you can see that for all these three, soft gas, desorption isotherm, and the desorption time, they are going to relate to the core testing. You will be collecting a core sample from the reservoir. You will be putting in the desorption canister. You will be maintaining a pressure gauge, and then with time you are going to collect the gas, and you will be able to measure that, okay, what is the total amount of the gases it is going to get. Okay, you are going to produce. Next is the relative permeability. Relative permeability, as you know, that whenever the term relative permeability is coming, the relative is coming, that means there is a different phases. Okay, so there is not only water phase, there is also a gas phase, or there is not only gas phase, there is also some of the water phase is possible, and that's why how the molecules are behaving, how the each molecules of the gases are behaving and competing with the water molecules. Based on that, the relative permeability will be dictated, and then the gas production will be dictated. So it should be taken from the core test and the production data. Production data means with time with the reservoir, because it will give you the relative permeability is related to the production data. So you have to see the production data and the core testing. The core test will give you the idea about the coal permeability, or the how much coal is permeable, and then with the production data you will be able to see that with this coal permeability how much of it is going to be used by this water or gases. Okay, then porosity, obviously for the core testing, from the core testing sending the helium gas. Okay, and you will be able to know about the total porosity, because helium will achieve the helium diameter is very small, so it will go to the molecular spaces, intermolecular spaces, which other gases may not be able to go, and so the porosity whatever is given by the helium, it is the maximum available porosity. Okay, at that point of time, because diameter of the helium is very less, it is approximately 26 nanometer, whereas diameter of the methane is 38 nanometer, and for carbon dioxide it is 33 nanometer. Okay. Next is the net pay thickness. What is net pay thickness? You know that depending on the coal seam, each of the coal seam is having some thickness. Okay. Now in your mining classes, you must have seen that the thickness, whatever the coal seam is having, in development you are only allowed to go for maximum seam thickness, or the seam height is limited to 3 meter, and in deep pillaring only you will be able to go at a single stage, you will be able to go by roof whitening process, you will be able to go up to 4.8 meter, and if you are going for the multi slice, you can go for single instruction, you can go up to 6 meter. Okay, if you are going for the multi slice, otherwise for single slice it's 4.8 meter. Okay, so like here also, that means there is a working thickness and there is an in situ thickness, or the original thickness. So here also, if you are going to produce the permeability, if you are going to test for the reservoir production, and you are going to take only some part of the seam, so in that case you don't need to consider the total thickness of the seam. You can take that much of the thickness which is actually giving your input for the production. Okay, so that part of thickness of the total thickness which is actually considered for your production, it's called the net pay thickness. Net pay thickness is defined as that particular amount of the thickness of the coal which is actually giving rise to the production, gas production. Because a coal seam thickness may be very high, okay, but all the part may not be internally connected. Okay. Next is the temperature. Temperature will be net pay thickness and temperature you will be able to get from the well log borehole data. Well logs mean borehole data log, or the borehole core section. Okay, like the way in the mining plans we are going to see that with depth how much borehole depth is drilled, what is the different strata, and what are the different strata, and with the different strata what is the exact thickness of each strata and the separation between them. So like that, in the borehole core testing or the well log testing, you will be able to see about the thickness of the individual seam and the coal seam. Temperature you can also measure from the borehole well log. Okay, Gas PVT properties. PVT properties means pressure, volume, and the temperature properties. Okay. It will be always, if you are going to do the gas analysis, you will be able to calculate the data or estimate the data about the pressure, at what pressure or the, at what volume of the gases are coming out, and at what is the temperature of the gas. Similarly, for the water PVT analysis, it is obviously, if you are collecting some water sample, then you are doing for the laboratory testing, and you will be able to do. Completion effectiveness. Now, completion is the well completion. Okay, once you have collected all those gases from a particular area of the reservoir, which is possible from a single borehole, because you know that if there are different number of boreholes, you cannot reach beyond a certain area from only a single borehole. And obviously there is always some overlapping, because two boreholes, whatever distance, if suppose the distance between two boreholes is 100 meter, so if you are going to consider equal zone of influence from the center of the borehole, so that means borehole number 1 having a 50-meter influence to the right of it, and borehole number 2 is having 50-meter influence to the left of it. Now these influences of two different boreholes, whenever they are going to meet, there may be some overlapping. Why? Because whenever you are going to drill, it is not exactly possible that the fracture will be retaining at the boundary of the 50-meter only. Sometimes, depending on the rock type, it may go beyond this 50-meter, or it may stop very early of this 50-meter. If it is going to stop very early to the 50-meter, then what will happen? That borehole zone of influence, if you are going to consider the 50-meter, within 50-meter, there is no fracture will be exceeding that 50-meter periphery from the center of the borehole. So beyond that, whatever rock strata will be lying, okay, that will be in the far field stress zone. Do you remember this concept? I have discussed with you near field stress zone and the far field stress zone. So if your borehole is having a very little influence or very little fracture surrounding to the rock strata, and it is not going to extend beyond 50 meter, so obviously there may not be any overlapping of this borehole influence to the other boreholes. But if the rock strata is so weak that there is an overlapping, that means for both the boreholes, the surrounding permeability, the surrounding discontinuities or the fractures are going to extend beyond 50 meter, then obviously the activity in one borehole is going to affect the activity in the other borehole also. So the stresses will be changing due to the activity of only one borehole. So then two boreholes will be in the near field region. Okay, so then the situation may be much more complex. If the situation is far field region and there is no such there is a mutually independent borehole, then things are very much sorted. Otherwise, you have to also think about the different borehole impacts. Okay, so in that case, what you can do, completion means the whatever gas production is possible through the one borehole, whatever you have taken, and then you are going to complete, you are going to shut down, you are going to stop this borehole because it is exhausted now. No water is coming out, water is already not there, and gases are also not coming out. Okay, and maybe at some point you may also stimulation, as I mentioned you earlier, that the stimulation is the process to enhance, to do some extra or external effort by which you are going to increase some of the permeability or the production parameter, so that you are going to get some higher production, okay, which are limited in the earlier cases. So stimulation, even if you have done stimulation, so after some time you will not be able to increase the permeability value, suppose. Okay, so then that borehole is called as exhausted, will be called as exhausted borehole, and obviously it will not be helping you for further production. So you will just complete. Why complete it? So that any surface water is not going to mix it with this, or any other unwanted garbage or any other unwanted drill cuttings is going to mix in the strata. Otherwise, the borehole will be locked, and again you have to clean the boreholes, or again you may need to drill the boreholes. Okay, so you may be shutting down by casing it. Okay, that is a different process. So shutting is the completion. Now completion effectiveness, that is again coming from the well test, how much the borehole is completed. Okay, and last point is the well drainage area. Well drainage area is already, you have seen earlier the effect of the well drainage area. It is called the spacing between the boreholes, because depending on the spacing of the boreholes, your drainage area of different boreholes, it may be overlapping or it may not be overlapping. One borehole area, nearby area, it can go to the different places at the different borehole area, or it may be limited to that area only. That is possible when you are having interconnected fracture system or interconnected permeability. Okay. So you will see that sometimes a term will come that the porosity, the single porosity is there, and then again the effective porosity. Why this effective porosity? Because effective porosity means how much of it is actually working. Okay. Sometimes the effective permeability is also existing. That means if permeability in the cold matrix, there may be different permeability options available. Okay, there are different fractures, but the aperture of the fractures and the persistence of the fracture may be very much less. But when it is becoming connected, then even if the aperture is less, even if the extent is also less, but due to interconnectivity, there is the porosity or the permeability of the cold matrix is also going to increase. So that parameter is called the effective permeability, which is much more higher than the original permeability. Okay, so these are some of the differences of the concept, and as you can see that they have discussed with some other parameters also. But if you summarize this, these are the generally these are the data by which you will be able to see the reservoir properties, and which will be able to see the production analysis, and then it will move to the next stage for the calculation of the gas in place. Okay, so after this let us going to check about the calculation of the gas in place. Okay, now whenever you are going to see the calculation of the gas in place, okay, so gas in place concept, okay, whenever gas in place means you are actually going to estimate what is the total amount of gas present in your reservoir. That is called the gas in place. Okay, whereas the gas content means what is the amount of the gases stored at this present condition. Okay, try to understand the difference between two terms. Gas in place means the actual or the original gas in place available, and then the gas content means at some particular condition, particular temperature pressure condition, what is the gas content, because the gas content is always depending on the pressure. If your pressure is going to change, if your structure is going to change, some of the gas will going to exceed. So your gas in place data may not be that much reliable for the estimation of the gas content. Okay, now there is another problem for this gas in place calculation, that even if you are having some data, okay, even if you are having some data, you know that the CBM reservoir may be a very huge area, okay, because it is going to be working a depth of maybe 2 kilometer or maybe some higher depth also. Okay, and depending on the extent, depending on the number of the boreholes, or depending on the connectivity of the reservoir, you may have some information about the particular borehole. Okay, and you have some borehole property, borehole information, you have collected some parameter. But then in between spaces, okay, suppose your borehole locations are separated by 100 meter or by 200 meter or by 500 meter, suppose. Okay, then obviously in between places, there will be some overlapping, there will be some changes, because it is totally natural. So there is always some chances of uncertainty about how much a data from a borehole, if you are going to do the analysis based on that data, how much it will be correct, because the data is going to change. Okay, just like the just like the reserve estimation, if you have done this, you might have the same problem, because then also you have to take some different sections. You may need to take the zone of influence. You may need to take different borehole color, different borehole properties, density, and with the thickness, and then only you are going to calculate. Okay, so like that, in between those boreholes, you don't know the nature of the seam. Okay, in mining, it may be possible because you may have the access, but in a petroleum industry or the oil industry, nobody is going to extract anything else than the boreholes. Okay, and once the borehole is there, you are just going to do the production. Okay, so there is a lot of uncertainty associated, by which you are going to consider the testing. Suppose you are going to consider any testing. Suppose you know that if you are going to do the rock sample analysis, you have some UCS testing, initial composite strength testing, you have some triaxial composite strength testing. Okay, so all of this you are going to maintain as per the ASTM standard, American Society for Testing Mineral Standards. Okay, we are going to follow that. But suppose these are for the experimental purpose, okay, for rock mechanics. But suppose whatever porosity you are going to do, porosity analysis you are going to do, whatever hydrolytic fracturing you are going to do, so for different industry, for different country, or for different local, okay, there are different companies which will be going to do the extraction or do the analysis. So all of them may not be following the same procedure. Okay, there may be difference in the concept, there may be difference in the standards they are going to follow. So in that case, there is also some chances of the uncertainty. And when you are going to compare a single borehole data with some different 2-3 companies, so obviously there is a mismatch. Why? Because the standards are different. Okay, so that much error you need to consider. Okay, now, whenever we are going to see the gas calculation, gas in place calculation, there are some different techniques. Okay, the first technique is the volumetric gas in place calculation. Why volumetric? Volumetric means you will be going to consider the total volume, not weight percentage or not any other thing, but the volume of the gas. Okay, just like that you will be going to measure the volume. Okay, and from the defined property, the equation is not so important, and for that you have to have some different parameters, and based on that you will be going to calculate the total adsorbed gas volume or the total storage gas volume. Okay, so what are the other parameters? They are showing you some equations, and they are going to show you some tables from the field reservoir data. I'd like to point out that you don't need to remind these equations, but at the same time you need to understand what are the parameters necessary for calculating this. Okay, suppose gas in place, they are going to calculate based on the volumetric gas in place calculation. Okay, what are the parameters is required? You can see the drainage area. Okay, the drainage area A, H is the coal thickness. This coal thickness may be the total thickness or maybe the net pay thickness. Okay, and as you know, you are going to calculate the gas in place, so obviously it should be the total thickness. Okay, because you are going to calculate the total reserve. Then phi F, it is the interconnected fracture, effective fracture porosity. Why it is called effective? Because how much is the connected. Okay, depending on the different porosity and different fracture connection, interconnectedness. So obviously the porosity will be much higher than the porosity of a single fracture. So that's why the interconnected porosity. Okay. Next is you can see that the interconnected fracture water saturation, because depending on the presence of the water, as you know, that if the moisture is present, the moisture is totally blocking the total amount of the spaces that the gases can be stored. So obviously you need to understand what is the saturation of the water. The less is the water saturation, obviously the gas can be stored. So, so obviously there is the more chances of the gas to be stored. Okay. Next is the BGI. It is the gas formation volume. What is the gas formation volume? That means whether at some particular pressure, okay, at some particular pressure, how much gas you can recover with the different place with a particular condition, whatever gas is there, how much of it you are going to recover. That is going to give the gas formation volume. Then CGI is the initial sorbed gas concentration. Okay, you can see here it is depicted. CGI is depicted as dry ash-free coal. Okay, so dry ash-free measure means you have to remove out moisture, you have to remove out ash content, and then only you will be reporting as a dry and ash-free. Okay, that basis. So CGI is the initial sorbed gas concentration. Okay, and then coal density, the fraction of the ash percentage, okay, in the total coal, the weight fraction of the moisture, and then some of the conversion factor, which is going to change from the imperial factor to the CGS system. Okay, so these are some of the factors. These are some of the parameters by which we are going to calculate the volumetric gas in place calculation. Okay. Next consideration is the you will see that in this data also they have also given some data, which is earlier tables are going to give you some data, or maybe in the next table also they are also going to give you some data about the field data about the volumetric calculation. You can see that based on different zone they have calculated the drainage area, the coal thickness, the formation volume factor, the cleat porosity or the fracture porosity, and then the water situation. Okay, so these are some of the data they have collected. Then again, from other areas, okay, what is the ash content, what is the moisture content, fraction means percentage. Okay, how much is the, with the total coal, how much percentage is the ash content. Okay, so in a ratio of this. Okay, and then you will see that for volumetric calculation they are going to estimate the total gas in place by summing this fracture gas in place, okay, and the soft gas in place. Now the soft gas in place can be estimated by the dissolvation canister testing, how much gases are going to dissolve, okay, and the fracture gas in place they are going to measure it from the values of the how much porosity, how much saturation is there, how much is the total effective porosity present. Okay, so from there they are going to estimate the total gas in place. Okay, and see there are three number of boreholes or three zones are present. And for each of the zones they are going to calculate. Okay, you can also see that for some particular second zone the fracture gas in place is 0. So there is no gas in the fracture. Why it is possible? If the fracture is very much connected and the fracture mouth is open, it is going to be connected with the borehole at some point. So what will happen? The borehole is going to be connected with the surface, which is going to open at the atmospheric pressure. So the moment your fracture is going to connect it with the borehole, so your gases which are present there, they are going to be directly going to be reduced at the atmospheric pressure. Okay, so whenever it is going to reduce in the atmospheric pressure, so it will be soon dissolved. Okay, the fracture or the fracture gas in place which is there in the free state, it is already escaped, and in the meantime the soft gas concentration what are there, the soft gas concentration due to the reduced fracture pressure, due to reduce atmospheric pressure, because it is going to be connected to the surface, so its surrounding pressure is also going to reduce. So obviously whatever gas disruption will take place, some of the gases, whatever the gas solved gas in place will be shown, this is already some reduced value of the dissolved gas, because as it is going to be connected to the surface, some of the gases are already dissolved. Okay, so this is the remaining value, because it is already 0, the reservoir pressure is going to reduce, so you cannot control the gas disruption. Okay, but if it is not going to be interconnected, then obviously your fractured gas in place will be, you will be able to estimate, and in your sorbed gas in place or concentration also it will be remaining intact because there is nothing to move. Okay, so summarizing this, you are going to have some information about the gas in place. This is the first consideration, volumetric consideration. Okay, which is totally based on some parameter, and you are going to calculate the volume of the gases present. Next concept is the material balance calculation. The material balance calculation means you are going to, and this is given by a scientific king, okay, some researcher. So you are going to get the idea about production, or before pressure change and after pressure change, or before the any sensitive parameter issue, okay, any escape or any fracture water production, or after that. So this is actually the most common method. You will see later that this is actually the most common method we are going to use, and with the help of the real gas law, which is the PV is equal to nRTZ, pressure, volume, and then N is the mole fraction, R is the gas constant, universal gas constant, T is the absolute temperature, and Z is the gas compressibility. So this is our base equation to estimate the total amount of the volume absorbed or the total gas content are staying there based on the applicable of the real gas law. I'll show you later that how this testing and the calculation is done. Although it is very much complex, but if I show you the step-by-step process, you will be able to understand. Okay. Now, as you have seen that for gas in place calculation, if you see the reservoir data, as we have discussed that the reservoir data is required and the production data is required. So as you can see that they have shown you some data, table 3.6, you can see they have shown you some data. Okay, and you must notice some units also. Okay, all these are in the imperial units or the FPS system. So you can see that the net coal thickness, initial reservoir pressure, initial water saturations, everything. Okay, you can see that the initial water saturation is given as 100%. So the fraction is 1, totally filled with water. Okay, so now you can understand that the reservoir is totally filled with water. That means it is totally saturated with the water. So obviously, the moment you are going to reduce the pressure, the moment you are going to take the water, okay, water saturation will going to decrease. But at the same time, gas saturation is going to increase. Why? Because gases will not come out at the very beginning, but the gas saturation will increase because the gases will be remaining intact, but the water is coming out. Then you can see that the water compressibility, pore compressibility, ash content, how much is the moisture content value is there. Okay. Now you must understand that obviously this moisture content and the initial water saturation are two very different things. Okay. Don't mix up these two. Moisture content and the water saturation, these are two very different things. What is very saturated with the water, whereas the moisture content means that moisture is also going to be take place. Moisture is also going to be stored, and that moisture content is 3% already. Okay, the in situ moisture content. Then the coal density, the formation of volume factor, the effective porosity, and all other conditions they have given. Acha. Standard temperature they have given here is the absolute Fahrenheit scale, which is called the Rankine scale. You can see 520 degree R. It is the Rankine scale. Okay. You must remember about that. Whether in a CGS system, if you are going to consider, it is called the Kelvin scale, SI system, whereas for the Fahrenheit, it is the Rankine scale. Okay. I hope you remember. You must have read this in the 12th class of physics. Now this isotherm parameter. The isotherm parameter, as it is can be coming from the resorption isotherm, or it can be tested in the laboratory from the core sample or the powder sample, and these parameters can be identified or estimated. Now these two parameters are very new to you: Langmuir pressure and the Langmuir volume. What is Langmuir pressure? What is Langmuir volume? The Langmuir volume is defined as the maximum volume of the gas that can be stored into the coal or reservoir at an infinite pressure. If you remember the shape of the graph, okay, you will see that with increasing pressure, x-axis is the pressure and y-axis is the gas adsorbed. Okay, so the gases and gas adsorbed graph is going to be flatter with the pressure. But after some time, if at infinite pressure, you will see that it will not increase beyond a certain point because it will be reaching a constant value. Okay, and this is the maximum value. That maximum value is called the Langmuir value, Langmuir volume after the scientific, after the scientist of Langmuir. Okay, after the scientist named Langmuir, and sometimes this graph is also called the Langmuir isotherm graph, Langmuir type 1 isotherm graph after his work. Okay, so the Langmuir volume is defined as the maximum volume of gases, the maximum volume of gas that can be stored, that can be absorbed by a coal at an infinite pressure. And the Langmuir pressure is defined as the pressure corresponding to the 50% of the total volume. The Langmuir pressure is not the same definition as the Langmuir volume, but the Langmuir pressure is defined as the pressure corresponding to the 50% of the total Langmuir volume. That means at L50, VL, so Langmuir volume at 50, okay, 50% of the total Langmuir volume, whatever pressure it is going to be shown, that pressure is going to be known as the Langmuir pressure. So if you see any isotherm graph, let me show you. Suppose this is another isotherm graph, okay? So at this pressure step, okay, you will not be able to see the Langmuir volume because the gases are still increasing. With increasing pressure, the pressure is and the gas constant is still increasing, so gases are going to absorb. If not, then it will be becoming flatter. So for the time being, let us assume that after this point, after 800 psi pound per square inch absolute, okay, absolute pressure, we are going to get a flat line. So obviously, as per the definition, we are going to consider that this point, whatever is the maximum adsorbed gas content is showing, it is the Langmuir volume. So the total range of the Langmuir volume is becoming from 0 to suppose 500. Okay. Now the Langmuir pressure is going to be rated as the half of this L50, 50% of this total volume. So if you are going to say this is the total volume, so 50% of this may be coming as, suppose this is 500. So let us come to the 250. This is 250 means. So 250, at this 250 volume, what is the corresponding pressure you are getting? Maybe approximately 200 psia. So this 200 psia is the PL pressure of the Langmuir L50. So these parameters are also called as the VL and PL. VL is the Langmuir volume, PL is the Langmuir pressure. So VL is defined as the maximum pressure, whereas PL is defined as the pressure and the gas pressure at the 50% of the total Langmuir volume. That means 50% of the total Langmuir volume is this 250 approximately, and at this 250, whatever gas pressure is going to show, this is called the Langmuir pressure. Okay, not the total pressure, mind that. Okay, so now if you see these two pressure, these two identification, these two parameters are going to give you the shape of the graph. Okay, because if the shape of the graph is going to change, suppose if this is the shape, this is the shape of the graph, but I am telling, suppose there is a new graph which will be like, it is going to like this way and then becoming very much flatter. So in this case, you will see, suppose the graph is showing like this. Okay, it is going to steeply increase like in this direction. Sorry, it is going to increase in this direction very steeply and then becoming very much flatter right now. Then how you are going to calculate? So you will see that although the maximum pressure is reached here, but half of this will be reaching like this point, Okay, half of it will be coming as this point maybe, and according to this the pressure will be coming as like this. It will be coming as approximately 100 or so. Okay, because the graph has become steeper. So what is the importance of this Langmuir pressure? If the graph is more steeper, so obviously you will see that at some lower pressure zone, some of the very high disruption will take place if the graph is becoming very much steep at the lower pressure but very flat at the higher pressure. So to reduce very high amount, to reduce the pressure, if you are going to reduce the pressure, very little amount of the gas will come. Okay, whereas at some very lower pressure, the moment you are going to reach nearly 150 or so 100, then only your gas production will reach the maximum. But this type of graph is not required. Why? Because you have to reduce from 800 psi to only 150. After reaching only 150, your gas production will be optimum, or gas production will be more or less stable. So with 650, from 800 to 150, with 650 psi, your gas production is very less. So you are not getting any production. Whereas if your gas is becoming much more flatter, what will happen? The moment you are going to reduce the pressure, you may find that after some time your gas production will start, because if it is the flatter one, as you are going to reduce the pressure, you are going to get the gas production. Okay, so the more flatter graph is the more suitable for the gas production. Okay, throughout the stable gas production throughout the time. Okay, and then you can see isotherm. This is called the isotherm parameter: Langmuir pressure, Langmuir volume, initial adsorbed gas concentration, which you can take some value, or maybe you can take from the disruption intensity testing. Okay, for simulation you can give the value from whatever you have taken from the laboratory testing. Okay, initial gas concentration. And then the Z factor. Z factor is the compressivity factor. That is, at some temperature, at some pressure, this compressivity factor is going to be defined. And let's see the production data, how much production data you need to give. See the reservoir pressure. Okay, reservoir pressure means what is the initial reservoir pressure, and then the water production. Okay, standard trillion barrel. STB means standard trillion barrel, not standard trillion feet like that. Okay, it is the barrel. Then water influx, how much water is you are going to flow. Okay, the water influx is going to rate. Okay, how much water you are going to rate with time. Cumulative gas production, double M, you can see, so it is the billion one. Okay, gas Z factor dimensionless, compressivity factor is always dimensionless. Okay, and what are the other assumptions you are going to take? Okay, so with this data you will be able to discuss, or you will be able to estimate about your total gas influx. Okay, now let me tell you that before you are going to do any type of the concept, you have to have some assumptions. What are the assumptions? For material balance, also for production data, for volumetric calculation, you may have seen that you have to take some of the parameters. Okay, these are some of the parameters you need to assume. Okay, based on the equation. For material balance equation, what you need to do? For material balance equation, you need to have some of the assumptions. What are these? Some accurate estimation of the current average reservoir pressure is required. You have to estimate what is the actual, not actual, maybe the average. Okay, so that you can actually going to calculate that at this much of pressure, this much of gas content is supposed to have. Okay, then some of the reservoir properties which you need to require for calculation. Okay, you need to calculate that. Then how much saturation is there? Okay, how much water influx? Okay, water influx, that means how much rate of quantity, Q, meter cube per second, how much quantity is coming, that you need to understand. Okay, depending on the pressure, depending on of your channel, okay, pipe or the borehole diameter. Then the Langmuir equation accurately describes the gas resorption characteristics of the reservoir. The Langmuir equation means there is an equation, I'll show you later, based on which you will be going to calculate the Langmuir volume and the Langmuir pressure. Okay, so you have to have certain assumptions, but as I have mentioned that there is always some uncertainty related to the fact, because the coal is very much anisotropic, it is heterogeneous, okay, it is very much natural, and you cannot have, you don't have any control on the deposition and the different properties of the coal and the reservoir. So one borehole parameters that is suitable to give you some very good estimation of the gas in place. The same parameter, if you are going to use it for the other borehole, that may be wrong. So again, for another borehole, you have to have the different parameters which is suitable for that particular borehole. Okay. So these are the two different methods, and another method is the simulation. Simulation you may not be knowing now. Simulation is the computer simulation which is done by the iterative process. Some algorithm or some technique is there by which you are going to, suppose there are 20 parameters, you are going to change only one parameter and giving the 19 parameter intact, and then you are going to see the results. In the second time, you are going to change parameter number 2 and all the other 19 parameters are going to remain the same, and you are going to see the results. So this way, you are going to find out, as there are different parameters and very large number of data are available. So it is not possible to do these things by manually. Okay. So the computer reservoir simulation models are available. There are some different softwares are also available. With those softwares, you will be going to very accurately, you will be able to see how a small variation of some parameter are going to affect your production. Sometimes it is going to affect a very huge amount, sometimes it is going to be independent of it, and sometimes it is going to change very lightly. So from that idea, you will be able to say that okay, this parameter is not that much significant for the production from this particular reservoir. Okay. So let me stop you at this point. In the next class, we will be starting with the analyzing and how much we are going to do the forecasting of the production. So if you are having any question, you are open to ask questions. Anyone?
Sir, can you repeat, sir, Langmuir